Hello, welcome to 2H TV. In today's tutorial, we are going to look at heat and thermodynamics, and we are looking at a subtopic under it, which is measurement of heat capacity. So we are going to look at measurement of heat capacity. Okay, so let's look at what heat capacity is. Then we look at what specific heat capacity also is. So heat capacity is simply represented by a capital letter C. So heat capacity is defined as mathematically the quantity of heat, right, required to raise the temperature of a body. So to raise a temperature of a body by 1 Kelvin, so 1 Kelvin or 1 degree Celsius. So mathematically, heat capacity is simply the quantity of heat required to raise the temperature of a body. Then the temperature is either in Kelvin or degree Celsius. So this is heat capacity. Let's look at specific heat capacity. Specific heat capacity is mathematically represented by a small letter C. So it is defined as the quantity of heat required to raise the temperature of 1 kilogram. In this case, there is 1 kilogram, so a mass within a temperature of 1 Kelvin or degree Celsius. So small c is specific heat capacity, capital C is heat capacity. So now that we established that capacity is capital C, while specific capacity is small c, and specific heat capacity involves mass, whilst heat capacity does not involve a mass of a body. So take notes of that. We will be hearing of these terms while we try to solve questions. So in the first formula, if you make Q the subject, which is quantity of heat, you get Q now is equal to change in temperature multiplying specific heat capacity. If you make Q the subject in the specific heat capacity equation, you'll get Q now is equal to specific capacity multiplied by the mass multiplied by change in temperature. So take note of that. Okay, so fast forward, let's touch on other terms that we will be coming across while we try to solve practical questions under measurement of heat capacity. So let's look at what let's look at change of state, right? So we have change of state, change of state. Okay, so with the change of state, we have sensible and latent heat. So we have sensible and latent heat. So let's look at what sensible heat is. Sensible, as the name suggests, something sense, meaning it is sensed to temperature. So sensible heat are the type of heat that changes the temperature. So sensible change in temperature without change in state. So change in temperature without change in state. Okay, then when you come to latent heat, so with latent heat there is change in state. So change in state whilst there is no, so without change in temperature. So take notes of all this. So the clear difference between sensible and latent heat is that for sensible heat, there is change in temperature without change in state, whilst latent heat, there is change in state without change in temperature. Take note of these terms. We'll be using them while we try to calculate, as I mentioned earlier. So let's look at the mathematical representation of latent heat of fusion and latent heat of vaporization. Okay, so with the latent heat, we have two types. Okay, we have the latent heat. So for latent heat, we have two types. We have latent heat of vaporization, and we have latent heat of fusion. So take note of that. So let's look at what latent heat of vaporization and latent heat of fusion is. We said that latent heat is simply a type of heat that it results in change in state without change in temperature, while sensible heat results in change in temperature without change in state. So let's look at latent heat of vaporization. So latent heat of vaporization is defined as the quantity of heat required, right? The quantity of heat required to change the mass of, so it's the quantity of heat required to change the mass of a body. So to change the mass of a body at its boiling state, okay, at the same temperature. So if we make Q the subject, our Q, which is quantity of heat, now is equal to latent heat of vaporization multiplied by the mass. So get this equation in mind, that anytime you are tasked to calculate quantity of heat and they've given you latent heat of vaporization, this is what you use. Now let's look at latent heat of fusion. Latent heat of fusion is also known as latent heat of melting. So latent heat of fusion is the quantity of heat required to change a substance from its solid state to the liquid state. Okay, so to change a substance, or to change one mass of a substance from its solid state to the liquid state. So when you make the Q here the subject, you get latent heat of fusion will be multiplied by the mass. So this is another equation. Okay, so latent heat of fusion and latent heat of vaporization are types of latent heat. Okay, so keep this. Determining specific heat capacity, there are a lot of experiments that are usually carried out. So what we are going to do is that when the question is given, it doesn't follow one thread of solving, so we try to tackle each question under the various form. You can determine the specific heat capacity of a substance using the electrical method. So you see a specific capacity equation given, and they'll be giving volts and all that inside, meaning that they use the electrical method. You can also use the method of mixture. So specific capacity can be determined using the mixture method. This is where you see an ice being given, or a solid substance is given and is being placed in a calorimeter and all that. Then a question will be given and you'll be tasked to determine the specific capacity, and it will contain vaporization. So vaporization. So we try to tackle each question under these various method of determining specific heat capacity of a substance. Okay, so before that, keep in mind that in specific heat capacity, or in determining specific heat capacity, heat that is loss is equal to heat that is gain. Okay, so keep this principle in mind, that heat loss is equal to heat gain. So under each of the various ways of determining specific heat capacity, there are different ways of doing it. So once you grab the understanding that when a specific heat capacity equation is given, it doesn't follow one thread. It's up to you to determine whether it is vaporization method that was used, because it has its way of solving. The electrical method has its way of solving and all that. So let's look at this question. So question, like I said, the question one is saying that calculate the heat required to convert 2 kilograms of ice at negative 12 degrees Celsius to steam at 100 degrees Celsius. You have been given the specific capacity of water to be 4,200 joules per kilogram per Kelvin. Then specific capacity of ice is 2,100 joules per kilogram per Kelvin. Latent heat of fusion is being given, latent heat of vaporization. So you know that latent heat of fusion is the quantity of heat required, right? So the quantity of heat required to change 1 mass of a substance from the solid to the liquid. Then vaporization, something from vapor, so vaporization from liquid to steam. Okay, so take note of the basic terms that we talked about. Then the question 2 also says that a refrigerator can convert 400 grams of water at 20 degrees Celsius to ice at negative 10 degrees Celsius in 12 hours. Find the average rate of heat extraction, the water in joules per second, right? Specific capacity of water is given to be 4,200. Specific capacity is given to be 2,100. So before we solve this question, let's understand the various phases that will occur, right? So in this video, we are really not going to solve the whole thing. Let's look at the various phases that would occur in an ice being at negative 12 degrees Celsius to steam at 100 degrees Celsius. We'll look at the various steps or phases that occurred. Then in the question 2, we are going to look at it as it initially was at 20 degrees Celsius to ice at negative 10 degrees Celsius. So let's just look at how we will convert the processes that will occur, the various processes that are going to take place for an ice which is at negative 12 degrees Celsius will become 100 degrees Celsius at steam. Okay, so let's look at that quickly. Let's do that here. So we just pick out this to draw the chain. So that ice at negative 12 degrees Celsius to steam at 100 degrees Celsius. So ice, the ice is at negative 12 degrees Celsius. Ice to 100 degrees Celsius steam. You know, it has to pass through some phases, some processes before an ice at negative 12 degrees Celsius would become steam at 100 degrees Celsius. So the first phase is going to undertake the first phase that will be taking place. So the first phase, so step 1. Okay, so step 1, the ice was at initial temperature of negative 12 degrees Celsius high, so it will now come to melt down to 0 degrees Celsius, sorry, 0 degrees Celsius ice. Okay, so this is the first step that is going to occur. Now the step 2 is that now it is 0 degrees Celsius ice, so 0 degrees Celsius ice, so it's now melts to a state where the ice becomes water, so 0 degrees Celsius water. Okay, so this is the step 2. So step 1, negative 12 degrees Celsius ice, it will now come to 0 degrees Celsius ice. Then from 0 degrees Celsius ice, it will now move to 0 degrees Celsius water. Okay, then the step 3 is now 0 degrees Celsius water. So before a substance or water begins to boil, it must start from 0 degrees Celsius water. So 0 degrees Celsius water now to 100 degrees Celsius water again. Okay, then the last step, which is step 4, would be that once it is 100 degrees Celsius water, it will now move to 100 degrees Celsius steam. So the various phases that would occur for an ice at negative 12 degrees Celsius ice to 100 degrees Celsius steam involve 4 phases. Okay, the first one is that it has to melt, right? The ice at negative 12 will melt to 0 degrees Celsius ice. So in a situation where it becomes an ice, then a different step follows. From the ice now, it will reach a point where you will not feel ice in the water, right? So 0 degrees Celsius water. So water begins to boil at 0 degrees Celsius water. It can't boil at 0 degrees Celsius ice. That's why it must be converted from ice to what? Water. Then water now will be now converted to 100 degrees Celsius water, right? So at 100 degrees Celsius water, so this is water. Sorry, this is water. Take note. So at 100 degrees Celsius water, it will now come to 100 degrees Celsius steam. So these stages are very, very important. You need to grab the understanding before solving any question relating to this standard or this format. Okay, so if you look through critically, you could see that here there is a change in temperature. So this is what a sensible heat. Okay, now the step 2, from 0 ice to 0 again. So 0 to 0, there is no change in temperature, so change in state. So this is a latent heat. Now which latent heat is this? Is it latent heat of vaporization, of latent heat of fusion? So the step 2 is the quantity of heat there will be mass multiplied by the latent heat of fusion, which is also known as latent heat of melting. Okay, so you could see that the ice and then the water are at the same temperature, no temperature change. Now you come to step 3, you could see that from 0 degrees Celsius water, it then moves to 0 degrees Celsius, 100 degrees Celsius water. Okay, so there's a temperature change, so it becomes a sensible heat. Now step 4, the temperatures are the same from 100 degrees Celsius water to 100 degrees Celsius steam. You could see that it is a latent heat, right? So which type of latent heat is this? Is it latent heat of fusion or latent heat of vaporization? So the thing was in water state, then it became steam. So the quantity of heat would be mass multiplied by the latent heat of vaporization. So this is for step 4, step 3. So try to understand this concept very well before we try to solve. So we look at the second question. We are going to try to just write down the phases so that in our next tutorial we'll look at how to solve it completely. So the second question also states that the water was at 20 degrees Celsius, then it became ice at negative 10 degrees Celsius. So from 20 degrees Celsius to ice at so this water to ice at negative 10 degrees Celsius. Okay, so in this case the temperature is now from a positive side to a negative side. So what you have to do is that let's look at how or the various steps that will be involved for water at negative for water at 20 degrees Celsius to move to a temperature of negative 10 degrees Celsius. So the first step, so let's look at step 1. 20 degrees Celsius water. It will now move to 0 degrees Celsius water. Okay, so step 2. From 0 degrees Celsius water, it will now move to 0 degrees Celsius 0 degrees Celsius ice. Okay, so right from step 3, let's look at how. So from 0 degrees Celsius ice, we will then move to negative 10 degrees Celsius ice. So this is the phases that occurred. Okay, so take critical look at it. The first example, it was from negative 12 degrees Celsius ice to 100 degrees Celsius steam. So from ice it must change from negative to 0 ice, then 0 ice to 0 water, then 0 degrees Celsius water to 100 degrees Celsius water, then 100 degrees Celsius water to 100 degrees Celsius steam. And we established that there were 2 instances where the temperature remained the same. So temperature remaining the same, you check whether it's either melting or evaporating. When it is melting, then we said it's latent heat of fusion, but when it is evaporating, then we said that it is latent heat of vaporization. So when you checked the second example that we did from 20 degrees Celsius to negative 10 degrees Celsius, we established that it is from 20 degrees Celsius water to 0 degrees Celsius water, then from 0 degrees Celsius water to 0 degrees Celsius ice. Okay, then 0 degrees Celsius ice to negative 10 degrees Celsius ice. You could see that the second step, the temperature is the same. Okay, so once temperature is the same, it's up to you to determine whether it is latent heat of vaporization or latent heat of fusion, because it is the latent heat that results in change in state without change in temperature. Okay, so from 0 degrees Celsius water to ice, you could see that it will be latent heat of what? Fusion. It is not vaporizing. Okay, so take note and practice more examples on how to convert from a specific temperature to a given temperature. Okay, so in our next tutorial we'll be looking at solving practical questions and various examples under this particular subtopic under heat and thermodynamics. Okay, thank you so much, and I'll be meeting you in our next tutorial. Okay.